Welcome and thank you for joining us for today's webcast, Best Practices for LED Lens Design, sponsored by Lambda Research Corporation and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 60 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speaker. Michael Gavin is the Vice President of Sales and Marketing at Lambda Research Corporation. With over 30 years of optical engineering experience, Michael has vast experience designing and analyzing illumination systems and implementing stray light studies with various optical engineering programs, including Lambda Research's TracePro, TracePro Bridge, and Oslo programs. He's worked on some very high-profile systems, including a stray light analysis of the Hubble Space Telescope, the design of the light pipe for the second-generation Microsoft mouse, and the Bionics ear curate that won the MDEA Award for Design Excellence. So now I'd like to hand the webcast over to our speaker, Michael Gavin. Michael?
Thank you very much, Billy. Well, let's get going on the webinar. I'd like to give you some input on how to do LED lens design. And with that in mind, let's kick off the agenda for today's webinar. First, we're going to look at setting specifications for an LED lens design. We're going to understand why we create shapes and what TIR is, which is total internal reflection. We're going to understand some of the optical principles that we need to know to get the best design possible. We'll look at some basics of setting up a design, along with design tips to create the best system possible. And of course, we're going to have to go across the basics of a design. And then we're going to follow this up with 3 examples: a narrow angle downlight lens, which we'll go through and show several different examples of. And then we'll go through and optimize it. A collimated TIR lens, and finally for our 3rd example, a side-emitting or BATWING lens. And I'll follow up with some conclusions. So first of all, let's look at how we're going to set specifications up for an LED lens design. And the biggest thing is, what are we going to use as a source? Well, it's going to be an LED, of course. But how do we get it to couple light into the lens? And how do we get it to hit the objective that we set up in terms of a specification? So we're going to break this down into what type of angular output you're looking for, what type of efficiency do you want to get out of that particular lens, and how much power do you want to get to your target, if there is a target. And of course, when we talk about targets, they can be anything from power, for instance, on a roadway. We can talk about how the eye sees that particular light. So we're going to look at output specification in terms of illuminance, efficiency, angular output, uniformity, and of course, luminance or lit appearance. So let's talk a little bit about what's going to constrain our design. And we have to know a little bit about the optical principles involved in doing an LED lens design. And the first one is Snell's law. Then we should also understand Fresnel loss, and what is critical angle and total internal reflection. What does bending curvatures do for us? What is étendue, and how do we use that in a design? And of course, we'll put all this together to start looking at basic lens designs so that we can run them through our examples. There's also things where we're going to have single and multiple LEDs and what the advantages are, especially for color. Of course, I'm not going to have time to do all of these examples, so I'm going to throw in some verbal information a lot with these examples. And another thing we're going to look at is top emitting versus side emitting LEDs. Well, the design I'm going to go through pretty much the 3 examples that we're doing today are all with top emitting LEDs. But there are also great examples for doing side emitting LEDs. So you've got to look at that as well. So first of all, let's look at the 3 different lens systems we're going to go through today. I'm going to go through and walk through a narrow angle downlight lens. A narrow angle downlight lens can have anything from a 60-degree angular output to a very small, like a 15-degree output. Then we're going to look at a collimated TIR lens, which has a very small angular output and very high efficiency. And then we're going to look at the last one being a side-emitting lens, which is a batwing type example. We'll see how that throws light out to the sides and hopefully doesn't throw any light out forward. So to understand what's going on inside of these lenses, we need to understand Snell's law. This is probably the most important law in optics. And it really is the formula which describes how light interacts when it enters a material like glass or plastic. When light travels from one material into another, it gets bent and refracts at that boundary. We've all looked into an aquarium, and it doesn't always seem right because we're trying to place something in the aquarium, and we stick our hand in to go ahead and grab it, and we're off a little bit. Well, that's because of Snell's law. Light gets bent as we go into that interface. And so pretty much for a ray that enters a material like water with an incident angle into the material, it gets refracted into another angle. And that's defined using Snell's law. So let me give you an example. Let's once again take the water. For an incident ray entering the water at 45 degrees, we can find the refracted angle using Snell's law because the sine of 45 degrees equals 1.33 times the theta, which is theta r, which is the refractive index in the material, which is water. So that bending, 45 degree in, becomes 32 degrees in the water. And that's why we get that displacement. We're trying to figure out where things are in the aquarium. It's all Snell's law. This is going to happen in the lens that we're going to design. So we've got to keep that in mind. There's another thing. There's the definition of Fresnel loss. So Fresnel loss occurs when light crosses the boundary from one medium into the another. So in other words, when I go from air into plastic or into glass, there's a loss due to reflection at that boundary. And you lose it both entering the glass and exiting the glass. So if we do a calculation, it's pretty much the index of refractions minus each other divided by the index of refractions added to each other and then squared. If we do this particular equation for plastic or for glass, realizing that the index of refraction is about 1.5 for both glass and plastic and air, for glass and plastic, and air is 1.0, we get a Fresnel loss of around 4 to 5%. Now, this equation has been simplified. The sine of the angle has been taken out. So pretty much we're only applying this where rays are normal to the surface. But you get the idea. We're losing about 4 to 5% of the light as we go through each one of the surfaces of the glass or the plastic. So the best we're ever going to do in terms of efficiency pretty much with a lens is about 90%, because we lose about 5% at each lens surface, and that's about 10% of our light. So now we have a good idea what we can do in terms of creating a lens design. Well, there's some other things that can help us along with our LED lens design, and they include being able to use the critical angle to keep light to 100% reflect off of surfaces and send it where we want. And of course, this critical angle allows us to do total internal reflection. And TIR occurs when light passes from a medium of high refractive index into a media of lower refractive index. So glass or plastic into air. So we can use air as a reflector and reflect 100% of the light when it's greater than the critical angle. And I'm showing you an example here. So I've got light coming in from the bottom left-hand corner, and it disperses outward, and it hits this media. Now, if the angle is greater than the critical angle, the light's going to be reflected in TIRs. If it's less, it's going to go through. And so the critical angle for plastic or glass, where the index of refraction is around 1.5, the critical angle is usually around 42 degrees for most plastics and for the most common glass, which is BK7. So in this case, we see that if we can keep everything greater hitting a surface at than 42 degrees, we're going to be able to keep all that light, 100% of it. So pretty much, what does that mean? Well, if we look at a particular lens design, we're going to see that the critical angle and total internal reflection for a wedge that has a power, as we see in the bottom right-hand corner of this figure, is that all the light exits out when it's less than the critical angle, and it TIRs to the side when it's greater than the critical angle. So we can use this in our designs to put light where we want it, keeping fact of the TIR critical angle type situation. One more principle I'd like to go over is étendue. And étendue is a measure of geometrical efficiency. So if we call étendue G, it's simply pi times the area of the source, or the beam, times the sine squared of the half angle of the beam in degrees. So if we look at the example down here, I've created a tapered fiber. What happens is the tapered left end has a very large aperture, and the right side of the exit area is very small. So what happens is if I have a very narrow angular beam or almost collimated beam going in the left side into the left aperture, étendue says that it's going to have to come out this much smaller area with a much higher wide angle output. So this means that we can use this as well to force light into a much wider angle or a smaller angle, depending on if we want to use a tapered fiber or a tapered lens. So it's very well seen that if we keep conservation of energy here, we're going to see that narrow and large has to go to large and narrow on the other side. That's just the way étendue works. Well, now that we've got the principles down, let's look at some of the basics in doing LED lens design. The common materials for lenses are plastic or glass. And the index of refraction of the lens material is about 1.5. And this will affect both the coupling of light into the LED and the light going out of the LED, as well as the guiding properties inside the LED lens. And so we can change the surface properties of the plastic to either improve or worsen the performance, depending on what we're trying to do here. And it's all about how the light comes out of that particular lens. Best practices for a lens, of course, is to have very high polished reflected surfaces at the edges, the sides, and the in the out portion, output portion of the lens. Diffuse surface can be used, especially when we want light to exit in a very high angular output. With perfectly flat exit surfaces, light can TIR because they go past the critical angle and stay inside the lens and bounce back and forth and never really come out. So the lens will heat up and you won't get the light out that you want. But a diffuse surface will break up that output section and allow the light to come out. We can also use roughened or periodic surfaces, scattering dots, or breaks in the lens to force the light to exit. Because wherever the light is less than the critical angle, it's going to exit out. And so we can do that by roughening up the surface and giving it a surface that has different angular output areas to throw the light out. So how do we do all this? How do we keep track of it? Well, I use software, and I believe nowadays with how difficult it is to do LED lens design, you need some type of software to see interactively what's going on inside of the lens. You need to have material catalogs and surface properties that you can apply onto these lenses. And you want to be able to add to these optical properties. And once you get that capability to define all these things, and hopefully they're just pull downs and you can just find them and drop them onto your particular geometry, you can then have utilities that allow you to see the output. Say, for instance, if you're interested in following the IES LM63 standard, that utility is there to let you look at it and make sure it's correct before you, say, post the information to your website on how good your lens is. Of course, we also want to do Illumidat in the European community. And when we try to bring in this source, how do we define the angular and the spectral information for that particular source? We're going to want to digitize in the information in terms of the angular and the spectral type information that define that source. So we're going to get a utility that does that. And then we're going to see how valuable the capability to ray trace a lens is, to see where the light's going. Because visually, we can't see light leak out of a lens once it's manufactured. Of course, we can turn all the lights off and probably see the sides glow because it's probably got a roughened texture because of the molding process. But we really want to know if the efficiency of the light going through the lens is going to work for us, where it's going to go, and we can do that with an interactive ray tracer, which is software. Finally, when we've got all this information put together, we want to be able to set up degrees of freedom of the lens. Let it move around. Let the sides expand. Add power to a lens to send the light out where we want it. And we're completely in control of that. But it would be nice if an optimizer would come in and use some type of local or global minima scheme to set up a merit function that allows us to change the lens to try to make it better using that optimization process. So let's look at some design tips. First of all, we've talked a lot about the critical angle. So we want to avoid sharp corners because that's where light might just TIR and go into other areas that we don't want. We want to make as accurate a source model as possible because when we manufacture this lens, we want to have it be the same as what we simulated. To improve efficiency, we can use scattering surfaces where necessary, but we also don't want scatter to put light where we don't want it, so we have to keep track of that as well. We're also going to need to trace a lot of rays to get an accurate answer. If we're going into angular space, we're going to possibly have to trace millions of rays to look at some of the noise problems and at some of the maybe the possible problems of dark and light areas that we might see with this particular LED lens. And of course, color is also a big plus to look at here. Some of the LED lenses that I've seen have yellow rings on the outside due to the white LEDs that they're using. Tracing enough rays will let you see that color problem. So why is doing LED design so difficult? Should be pretty easy. I mean, we had an incandescent design, most likely we've been using it for years. Now we're going to switch to an LED. Why is there a difference? The big difference is that LEDs emit plus or minus 90 degrees. And it usually looks like a Lambertian curve, which means that it follows the cosine of the angle. So directly will be have the most power, and it'll drop off to about half power at 60 degrees, just like the cosine does. So if we want to create uniform angular and positional output on the output surface of a lens, we're going to have to take a hemisphere, put it out there at infinity, and look at what the power looks like in terms of angular space. And then we're going to want to look at it as it's seen from the front of the lens, as it's escaping out, and see what that looks like. So being able to do photorealistic rendering is going to be a big plus here if you're doing that type of analysis. So now that we've got the design basics down, and I've got some tips here and some ideas of what we're going to do, let's do our first lens example. Let's look at a narrow angle downlight lens. So let's look at a specification that we would set up for this lens. We're going to create a narrow angle output lens. So we want a target right in front that's going to verify that. And we're going to take our normal Lambertian angular emission from our LED, and we're going to tighten it up to about a 15-degree output. We're going to be okay with sacrificing efficiency to get this angular output. And a perfect example for this type of lens would be a MR16 narrow angle output lamp. Perfect for doing a spotlight in a display case onto a high dollar item, for instance, to see that. We're going to look at a couple of different designs here to find a local minima, which gives us the global minima. And we'll say that the lens is made out of plastic in this case because they're moldable. And we're going to have some interesting things going on inside of the lens to mold it with. So let's look at a possible starting design. We've got a wedge. So we're starting with a wedge shape here. And we have a little cavity so that we can place the lens right on top of the LED, which is probably going to be surface mount. So there's some area that is open around the LED. And for the sake of looking at the starting design, we'll say that it's a point source with a large angular emission. And we'll look at the rays in an interactive ray trace here. So we can see that we're getting most of our light out the exit surface, which is always good. And there are some segment points here that define that wedge. And we can see that it's going to be possible to pull on those pieces when we do the optimization to change the shape, because we are losing some rays out the sides, and we're not getting the collimation or the narrow angle output that we're looking for. So if we go through and we start looking at this in terms of what we're trying to do, we're starting with that rectangular wedge shape. we're starting with a design that narrows the angular output using the sides and using the top to send that area out narrowly. And then we're making sure that we're getting TIR off the sides, but we're also making sure that it's exiting out that exit surface. And we're getting good exit ray coverage across that whole exit surface. So using that interactive ray trace helped a lot here to make sure that we have a good starting design. And now we can start modifying that design. We can give it more capability. So for instance, if the exit surface I want to try and give a smaller angular output, I can give it power. And the outside areas I can leave planar for manufacturing purposes if I want to. But I can also let the design move around. So you're seeing little boxes that I've drawn in here. I'm going to let the points of this particular output face move around those boxes to see if I can get a better output while I'm optimizing. We've also noticed that the curvature has been added to the sides so that we get complete TIR and we don't have light exiting. So here's what we're going to start with in terms of a starting design for this particular narrow angle lens. So now that we've added the degrees of freedom and I've listed all the things that we've done here with that starting design, we can look at some output from that design. So if we do a full ray trace from the LED specifying the Lambertian angular output, we see that we get an angular output around 30 degrees, plus or minus 30 degrees, with an efficiency of about 45%. What's nice about doing the interactive ray tracing to start with a simple set of rays is to make sure you're in the ballpark. And we are here. We're getting close to what we're trying for in terms of our specification. If we then use the optimized starting design where we've added power to the middle section and curved the outside surfaces, we now see a great improvement. Our angular output is less than 12 degrees, and we still have that 45% efficiency. But we also notice, because we have the visualization of the rays, that the outer section is not really helping us here. The light is really going out at higher angles, and we're not being able to use that area effectively. So what we might want to do is go back and add some slope to that outside section to try to bring those rays into a smaller angular range. And you can see that we're doing that with the interactive ray trace here. So we've modified the outside areas to do this. Now, if we do a full ray trace, we're getting exactly what we wanted, which is about a 20-degree output, which gives us the MR16. We've got an efficiency of about 39% here, and this is the start of the optimization process. After optimization, we go down to a 14-degree because we're trying for a 15-degree, plus or minus 15-degree angular output, and we get 85% efficiency, and you can see the light going right to the lens. Remember, about the best we're going to do here is 90% because of Fresnel loss. So at 85%, we've got something that's very, very close to being the perfect answer to our narrow angle downlight. So now that we've gone through, we've successfully done that, looked at several different local starting points, and come to a global answer, we can look at a second example. The second example is a collimated TIR lens. And it's a little bit different, not much, from the last one, and we can build upon the last example to get here. So a collimated TIR lens creates a collimation. And so once again, we're going to take that LED Lambertian angular emission. I'm going to try to collimate it. And we're going to sacrifice efficiency if we need to get that collimated angular output. And this lens is perfect for trying to couple light into a fiber, going into a light pipe to do some type of mask to show some information to, say, an automotive driver or someone using a piece of machinery. And of course, we can do this into a whole bunch of LEDs, so we create an array of them to light up an area like a parking light or something where hundreds of LEDs will be beneficial. And we can look at several starting designs, but in this case, because of the length of this webinar, I'm just going to look at one starting design, and then we'll look at a final optimization. So instead of going with the wedge that we used last time, we can build upon that last example. And we can see that we've got good collimation in the center if we used a little bit of power on that top surface. But once again, we're getting poor collimation from the sides, although we are getting complete TIR. So if we look at our specification, we're going to need to add degrees of freedom to this lens to get us to where we want in terms of an output specification. So we started with that similar rectangular wedge We've added curvature to it. We've added variables to let it move around. The top surface, which is the exit surface, has been given a little bit of power to collimate the light. And we're going to add variables to allow the design to flex to get to our answer. And we're going to make sure that we put a target in front so that we can see what the collimation looks like on a target right in front of this particular LED and lens. So if we do that, once again, we're going to get an angular output less than about 30 degrees here, so plus or minus 30 degrees with 49% efficiency. This is the start of what we're trying to do. If we optimize this by putting in the variables that I've shown you, we can get a much tighter angular output less than 15 degrees with 87% efficiency. But I want a collimation, and we see that we're not getting that. And the reason why we're not getting that is that we have to give it more degrees of freedom. The outer section should probably be a different segment than the intersections of the exit surface of the lens. And so as we go through, we can go back to the interactive ray trace, use that to go through and perturbate the design so that we start getting more collimation. Because really, we'd like to see a plus or minus 5 degrees with almost 85% efficiency. And we need to do that to continue on. So due to time constraints, I'm going to jump to a much more interesting example. This is a third design example. It's a side-emitting or batwing lens type example. And what we're going to try to achieve here is that instead of sending the light out the top of the lens, we're going to send the light out the sides of the lens. So we're going to try to design a 70-degree angular output with like a 10-degree band around it. And we're going to have to do some really interesting things to take the LED's standard Lambertian angular emission and to send it out the sides. So we're going to have to use TIR. And we're going to try to minimize the light that comes out directly out the lens because we don't want to see it. So what would be a perfect example for this type of lens? If we were creating a crosstalk where we're going to embed the lens into the roadway, and you'd want to have oncoming drivers and the people walking as pedestrians across this crosswalk to be able to see it. So we're going to look at a starting design. We're going to go ahead and optimize it. And we're going to see what we can find in terms of a best result. So what would a typical TIR design look like? Well, we're going to have angles on the top surface that meet our critical angle, and which means that we're going to have to be greater than the critical angle to send the light out the sides. Now, we're going to have a batwing design, and the angle of that top V has to be set so that it keeps critical angle, and that critical angle is at the desired 70 degrees coming out. So if we deepen the V, it's going to give us a different angular output as if we make the V more shallow. At the same time, we have to make sure that we keep TIR. And the sides have to be such that we don't want TIR. We want light to go through those sides. So in terms of looking at what a batwing starting design would have, we've got to force light out the sides. We have to make sure that the bottom and top portions of the lens let light escape out the sides while the top TIRs the light to those side areas. And we have to let the bottom let the light through into those areas. And the degree of tilt of the top surface segments should control the angle of the light exiting the lens. And so we have to make sure there's enough degrees of freedom to let the light, let that top surface flex to give us the angular output we want. And once again, we can use the interactive ray trace to go ahead and give us a really good starting design, which you've seen. And then we can use the full program to output the full angular emission and show us what that output looks like. So we start off and we see that the top segments are not putting the light out at 70 degrees, or pretty much around 60, and my angular width is way too large, around that 60-degree width, so I have a plus or minus 20 degrees instead of the 10 that I want. And then I've got light going out the middle section as well. That's a problem. So I think I did something wrong when I first set up the initial design. Because when I do optimize this particular design, I can't get it any better, and I'm still getting light leaking out the middle. So what's happening? Somehow there's something wrong with my middle section, but I am getting the angular peak that I'm looking at 70 degrees. So the starting design was good from that aspect, but there was something wrong that I did. And if I go back to the interactive ray trace, I find that I let the middle segment move around. So I actually created a flat segment during the optimization process, which allowed light to leak out. And here's the beauty of being able to go back and see the visualization of the rays during the optimization. I can see that I've made the mistake, and all I have to do now to fix it is to draw those segments together. And so I did that, and then I re-optimized, and we see the initial, that area at 0, which had a lot of power, has now completely almost gone away. We fixed that problem, and we now have a design that works, plus or minus 10 degrees around the 70-degree angular output. So I'm getting the side emission that I want. We can see this. I still am having a little bit of rays going out, but it's very difficult to take a LED Lambertian output and make it go all out the sides without a lot of tweaking. But we see we've gotten something very, very close to what we would like to see here. And we could do some further tweaking, and I leave that up to you in terms of trying out the program. But we've come to a very good answer here. So I'm going to now wrap this up with some nice conclusions. And in terms of, I found that the best practice is to start with a good basic design. And the way that I do that is interactively ray tracing the design and pulling on the segment and the control points to get something that works. So in other words, I have light going in the direction that I want, at the angular direction that I want, with at least a 10 to 20% efficiency. And that really gives me a feasible starting solution. At that point, I set up the variables that I'm going to use for the optimization process. How much am I going to allow the control points and the segment points of the design to move so that it's manufacturable and that it gives me the results that I want? And then I set up operands for my merit function. And these operands can be how much light I want on a particular surface. What type of angular output do I want to come out of the lens? What type of uniformity is important to me on either a surface or on the exit surface of the lens itself? And at that point, I'm ready to go off and optimize. And when I do this, I usually get a good result. When I start with something that's got a nice local minima, I go through and specify the variables to give me enough degrees of freedom. I go out and I allow the merit function to be possible. And then I use tools to verify what's going on. And these tools allow me to visualize rays to selected targets. I'm able to see power on a surface or a target or on a whole object. Having the capability to see power flow of light through a lens is really important in some cases to see where I'm losing light and where the light is uniformly on a particular surface. And of course, the angular plots are very important for us, especially in this case for the side emitting design, so I can make sure that light is going off. And for that third example, that was at 70 degrees. And if you can break down the paths, so if I go back and we look at what was going on in this particular lens, I had light coming out the top portion of the lens, the side portions, and the bottom portion. I can look at each one of those paths separately if I want to and make sure they're going in the right places with the right amount of power. And having the capability to have tools that allow you to do this are going to be important to make sure that your LED lens design goes the way that you want to and you get the results that you want to. So in terms of wrapping this up, we're going to go to the question and answer session. And I wanted to thank you for attending the webinar. And I want to also offer you a free 30-day trial of the program that I happen to use, TracePro. And you can sign up for this at our website, lambdares.com/trials. And if you have any particular question, once again, I'm Michael Govin. I'm the Vice President of Sales and Marketing for Lambda. And my personal email address is mgovin@lambdares.com. Or give me a call at 520-574-0150, and I'd be glad to discuss any of your LED designs, lens designs. And with that, I'll give this back to Billy for the question and answer session.
Thank you, Michael, for giving us that look into LED lens design best practices. Now it's time for our question and answer part of the presentation. So if you have a question, you can submit it right now. We'll answer as many questions as we can, and if we don't get a chance to answer your question by the top of the hour, our sponsor will do their best to address it after the webcast. So the easiest way to submit your question is just to type it in the box at the bottom of your screen. Michael, we already have some questions that came in. The first question, what is the best way to enter a source for an LED lens design?
Well, usually the manufacturer has a nice specification sheet that specifies the angular output, the spectral information, and the amount of power generated by the LED. We have a surface source property utility that allows us to screen capture those curves, those figures that show both the specular information and the angular information, and you can drag and drop those right into our utility where you can digitize in that information in terms of the angular and the spectral information, and that becomes your source inside the program. And this is really easy to do. There's a couple of videos on our website, and I'd say the whole process may take a couple of minutes for as many LEDs as you possibly have. So we have some in the program, and it's easy to do it that way. But there's also a couple of other things that really go on here. You can use the physical geometry, which is shown in those manufacturer spec sheets, to put in the exact size and areas of emission and do it that way as well. And both of those give really good results.
What is the best efficiency you will see out of a typical lens?
Yeah, the best efficiency is going to be about 85 to 90% because you've got about 5% Fresnel loss in the lens itself. I think that it depends on the design. So for instance, for a side emitting, you're going to have less efficiency because it's very difficult to corral that light out. But if you're truly trying to get the light out the front exit surface, it is possible to get anywhere between 50 to 85% efficiency.
We have a question here. What about LEDs that have a different divergence in the vertical and horizontal direction?
That's a very interesting question, and pretty much what has to happen here is that you have to design for both the vertical and horizontal direction. And you're going to have to make an asymmetrical lens to do that because in terms of, is it a different divergence in the LED? If it is, then if you put a symmetrical LED, you're still going to get that asymmetry that comes out of the lens. But if you're trying to create a symmetrical output from a LED that has a different divergence in each direction, then you're going to have to create an asymmetrical lens, be it a cylindrical type lens, which would then have power in one direction that's different than the other direction to focus that light out to where you want it depending on the angular answer that you're looking for.
We've had a couple questions here asking about the availability of slides, and before I hand it to you, Michael, I just want to mention that our webcast will be available on demand at techbriefs.com in the webcast section of our site for the next 12 months. Do you have anything to add there about availability of slides?
Yeah, the slides are definitely going to be available for viewing, and you should be able to download those from the Photonic Tech Briefs website when you go to the link to view the presentation.
Great. Here's another question. Does the software allow for more than one light source, for example, combining multiple LEDs in a light pipe manifold?
As a matter of fact, it does, and I'm glad that we got this question because I didn't show it's very, very important to be able to do things like RGB LEDs, and you're going to have a different emission area for the red, green, and blue areas. And yes, the program allows you to couple in each one of those sources. You can look at them separately. You can also combine them to look at the color characteristics. And the TracePro capability inside of the program breaks up the light into different colors per wavelength, so you can track each wavelength as a function of the color of light it emits. And then, of course, you can add this all back in at any target and look at things like CIE XY or CIE UV type characteristics, and, of course, true color. Put it all together and look at a red, green, blue type representation, see what that looks like as well.
What is the best material to use as a lens? For example, glass, plastic, or is there another material that's best?
Well, in terms of if you're going to mold the lens, it's best, of course, to go with plastic because of the mass production, how easy it is to do. But if you've got thermal problems and you're going to be heating up the glass, is a much better way of going because the plastic, of course, has characteristics of changing color over time due to temperature type variations, whereas glass does not. Depending on the type of plastic that you want to use, you can select between polycarbonate or acrylic. And it depends if you're going to have this outside where there's a UV type problem, or if there's going to be something abrasive hitting the plastic. You would want to go with a plastic that is more resistant to abrasion if you're having that type of problem. So, for instance, if you're putting this LED lens on top of an LED and it's being flown on an aircraft, and you're running at 500 miles per hour, you're going to have something that is not going to have problems with abrasion of grit and things in the air as you're flying through it. So it just depends on where, in terms of temperature and in terms of environment, which one of those you're going to select for doing this type of lens.
We had a similar question to how do you pick a lens material so that its properties will not decrease over time?
Same thing. In terms of if you've got temperature type things, you're probably going to go with glass. In terms of if you've got abrasive type things, you're going to pick a harder type plastic that will not have abrasion type problems. And you can get this information from the manufacturer. They pretty much know what will work for you over time.
Michael, can you define a target light distribution and have the system optimize the reflector to meet the target goal?
Yes, very much so. So in other words, in your merit function, the operands that you want is you want to specify you specify a target surface, and then you optimize to see the light on that target in terms of the distribution that you want. And the program will perturbate according to the degree of freedom that you've given the lens in terms of its variables, and it will go and flex the design until it meets those goals, if possible. And that's the big thing, if possible. In a lot of cases, you might have to add some mechanisms to the lens to allow it, for instance, the side emitting lens that we did, to allow the light to go out the sides enough that you get the efficiency that you're looking for there. And of course, that's why you have a bottom and top section on that batwing design, because the light that goes directly out, you really don't have a lot of control of except for that one side. And the light that goes out the top, we have a second section that allows the light to TIR off that batwing design and off those top segments to throw it to the sides, which has a different profile than the bottom section does.
How do you deal with large surface area emitters such as 3x3 LED arrays?
So in terms of what we do inside of the program, you create that actual geometry, and you specify what the angular and the spectral information is from that geometry. So one of the things is a lot of these lens design things that I showed are really perfect for point source or very, very small LEDs. When you get to these arrays, which are large, a lot of the things that happen, you're now hitting the surfaces at different angles because of the large emission area. And so it becomes a much more difficult problem, and our efficiencies drop because of this. In a lot of cases, manufacturers or optical designers go with more LEDs with multiple lenses because they're breaking the optical principles that I presented in this webinar. So in terms of what we try to do here is that when we're using a large LED array, we try to use less areas of optics to use. And if we do it with gentler bends and less power, because we know we're only going to be able to do efficiency or where we want that light to go on a small area, and where large areas are going, we try to do less in terms of trying to move the light around. So in terms of a large LED array, it's a much more difficult design because we're using a broad source. And in a lot of cases, we break it down so that we have micro lenses over the different emission areas, or we have separate lenses over those arrays, and each one takes care of that design for that area.
Here's another question from an attendee. How is illumination affected by the distance of the LED from the lens?
One of the things is we're talking about coupling here. And as the rays go farther out, you've got a near field and then a far field type coupling going in. And so the distance, you're going to have the possibility of light not coupling into the lens because you have it farther away. So if you're looking for high efficiency, you want the lens to fit right on top of the LED. But in the case of having to have a distance away from it, you're just going to have to not worry so much about efficiency. And hopefully If you've got this type of problem, you're not looking at coupling 90% of the light through. You're maybe looking at coupling maybe 25% of the light through because you have a distance where the light is not going to enter and couple the lens. So dropping down the specification for efficiency may be your answer here. Or you may have to put a mechanism where you have reflectors or put TIR out at the edges with some other optic to then send that light into the LED, which is farther away, like a light pipe.
How is the lens designed based on the LED's wavelength?
Well, we just talked about visible here. And pretty much when we're designing in the 0.4 micron to 0.75 micron range, the index of refraction changes minimally for glass and plastic that we're talking about, polycarbonate, acrylic, PK7. They don't change much. And the design's not going to change that much based on that. But on the other hand, if we go into the IR wavelengths, then it's completely changed. Our index of refractions are much higher. Our Fresnel loss can be in the 30-40% range, and we have to take that into effect. Now, if we're just talking about the visible, then we're worried also about the prismatic effect. If you send light, collimated light, into a prism, it breaks up into the different spectral colors. Well, you could have the same thing happen here. If there is a large divergence because of the index refraction of that lens or because of faceting or things of that nature, we can get color effects. So we've got to be careful about that. And one of the nice things is that with software, we should be able, if we trace enough rays, to see those type of effects and be able to eliminate them by either making less sharp curves in the particular lens or by using some other mechanism like a texture to diffuse the light out to get rid of the color effect.
What is the best way to protect manufacturer LEDs from the outside environment?
Well, that's a good question. Usually it's a cover lens. That is a very, very hard material that is put on the outside if that is a problem. Or you have to use the hard, if you're doing plastic, to use the hardest plastic out there.
It looks like we have one more question here, Michael. Is there any way to roughly measure PAR in TracePro? I'm kind of stymied here. In terms of PAR, I think, are we talking about the PAR lamps in terms of their angular output? I'm not quite sure what is meant by PAR here. If the person would like to come back in and explain that a little bit more, I'd love to answer that one. Sure. So that attendee can write back in the question submission box.
And one of the nice things that I would like to tell you is if you may have questions, there are webinars on the Lambda Res website that address a lot of these issues. For instance, how to create sources, how to properly create sources, how to deal with large LED arrays. There's actually a lot of material on there that walks you step by step how to use the program to do that. And a lot of these, for instance, I have a PAR 38 example that shows you completely how to go from start to finish with a bunch of LEDs and create that particular output for that particular lamp. And it walks through the process as well as I just did with these 3 lens designs.
Thanks, Michael. We'll end it there. Your contact info is there on the screen. That'll conclude today's webcast. And again, if we didn't get a chance to answer your question, our sponsors will do their best to address them after today's presentation. So our thanks to Michael Gavin and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.